Welcome to Schulich UAV. We are a team from the University of Calgary, located in Canada. Today we're excited to share with you our journey of innovation to prepare for the 2024 AUVSI SUAS competition. Here's a quick introduction to the team we are planning on taking to the competition this year. We analyzed the requirements ensuring our UAV meets the competition's demands this year. With first-hand experience of the previous competition, we were able to more accurately create an outline of goals for the year. From our timeline and flight tasks, it's evident that our UAS needs specific flight time and speed to earn maximum points. We decided to establish a baseline distance of 15 miles, a maximum of 30-minute flight time battery capacity with a safety reserve, a typical flight speed of about 12 meters per second to ensure we meet all the waypoints, a maximum deployment time of 30 seconds for the payload, and a high payload capacity on board to reduce the total distance traveled.
Our UAV system has been carefully engineered and integrated with various technologies for optimal performance. It is a conventional quadcopter VTOL design featuring an Ares M900 frame and powered by a cluster of 6 LiPo batteries, supplemented by an additional LiPo battery to power the electronics on board. This setup grants us 60 minutes of hover time unloaded and is tailored for long-range photography missions. With a fully payload takeoff weight of approximately 10.10 kilos, our system is adept at carrying substantial payloads over long distances. To facilitate versatility and endurance, we incorporated a winch system mounted beneath the quad, integrated amongst electronics and batteries. This is to ensure payloads are delivered in an efficient and safe manner. For electronics, our setup utilizes a Raspberry Pi alongside a Raspberry Pi global shutter camera for high-quality image capture, while a Rocket M5 wirelessly bridges ensures reliable transmission of data to the ground station. The Pixhawk flight controller governs motor functions in tandem with ArduPilot and Mission Planner, ensuring precise control and navigation. Complementing this setup is an external ground control station, instrumental in receiving and processing image data to aid strategic flight planning and calling payload delivery instructions.
Our drone is equipped with a high-performance Raspberry Pi global shutter camera featuring a Fujinon DF6HA1B lens. This camera has a resolution of 1.58 megapixels, ensuring high-quality imaging of ground objects at our operational altitude of 85 feet. Designed for fast motion photography and machine vision, it minimizes distortion, crucial for AI applications in our specific use case. With a pixel size of 3.45 by 3.45 micrometers, it offers exceptional light sensitivity, allowing for short exposure times as low as 30 microseconds, thus making it ideal for high-speed photography. Compacted at 38 by 38 by 19.88 millimeters and weighing just 34 grams, it outputs RAW 10 data formats and utilizes a Sony IMX296 LQRC sensor with a 6.3 millimeter diagonal size. These qualities ensure that our drone can effectively capture and analyze ground data beyond altitude restrictions, proven and tested with high-speed flights with previous aircraft designs. Our system ensures reliable imaging and object detection and localization control capabilities. Image processing occurs in 3 steps: identifying bounding boxes of targets, classifying shapes based on shape, letter, and color, and converting pixel coordinates to latitude and longitude coordinates. Bounding boxes of targets and target localization employs a deep convolutional neural network model utilizing a single-shot detector architecture for fast, efficient, real-time performance. We retrained a MobileNet V3 model for this purpose, enhancing speed and reducing computational complexity. Bounding boxes are then processed by shape and letter classifiers, also leveraging MobileNet V3 for swift performance and reduced complexity. Color classification utilizes OpenCV with masking and filtering techniques. Pixel locations are determined using pitch, roll, yaw, camera lens field of view, and real-time drone location using map proxy. This enables precise target coordinate computation, with multiple detections of the same target being used to manage uncertainties. This is managed using control theory in the form of Kalman filtering or linear quadratic estimation for dynamic systems. Our imaging and ODLC system is complete and has demonstrated success with flight systems from previous years. Leveraging data captured by DJI Mini 2 camera drone, our machine learning model achieves over 90% prediction accuracy, validating its robust object detection and classification capabilities.
We recognize that complications in design can compound during integration, making the entire system unusable. For this reason, the payload system for this aircraft is designed around one principle: simplicity. The design itself consists of water bottles hung underneath the aircraft, contained by 3D prints to ensure that the bottles do not swing and disrupt the stability of the aircraft. The bottles are supported on their descent by stepper motors that lower them using a fishing line. As an aside, stepper motors are used for 2 main reasons: their ability to hold the payload in place just by being powered, and their precise rotation. These two factors ensure smooth integration with the rest of the aircraft systems. The biggest challenge with stepper motors is having them produce enough torque to consistently lower the water bottles while ensuring the descent velocity is acceptable. There are a number of methods that can be used to separate the bottle from the line once on the ground. They range from lowering a servo mechanism alongside the bottle to cutting the line on touchdown. Ultimately, we chose to use a gravity hook design. This design uses the weight of the bottle to seat it inside the upper hook, which comes apart when the bottle is being supported by the ground. Being space efficient and reliable with no moving parts are all advantages of this design. On the ground, the stepper motors are able to hold the weight of the bottles and allow them to descend in a controlled manner. With the mechanical design complete and set in stone, we plan to integrate and test the payload in the air in the time between May 1st and the competition.
We've implemented aircraft-to-ground communication hardware to optimize performance. Our setup includes a Rocket M5 for wireless connectivity, SICK radio telemetry for onboard communication, and an FrSky X9D L9R system for manual control. The Rocket M5 ensures reliable long-range connections for image transmission and payload drops. Ground tests confirmed its performance, achieving 40.5 megabits per second up and down with 1.8% packet loss at a range of 1.1 kilometers. For onboard communication with Mission Planner, we rely on SICK radio telemetry tested up to 500 meters with quick reconnection if connection is lost. SICK radio telemetry is not mission critical as flight planning is downloaded onto the PIC-SOC to serve as a failsafe. The FrSky X9D L9R system provides manual control for the safety pilot, tested up to 500 meters or 0.3 miles with no issues. Our communication system operates at 900 to 915 MHz for radio and autopilot control, 2.4 GHz for manual control, and 5 GHz for payload and data transfer. This year, we have decided to proceed with a multi-rotor quadcopter design.
When designing multi-rotors, frame size is one of the most important choices to be made. Using a small frame does ensure that we must conduct refuel landings and carry a smaller payload. However, this loss in efficiency is made up for in greater reliability. A quick overview of the aircraft shows that it is laid out from top to bottom as follows. A handle is placed on top for ease of transport along with the avionics battery. Then the main aircraft frame with the avionics and camera. Then a battery box for safeguarding the batteries in flight and in the event of a crash. Then the payload mechanism is below that. The frame itself is largely made from carbon fiber plates with 20mm carbon fiber tube, with fittings being made from aluminum. All bolts are secured in place with Loctite. While the aerodynamics of a quadcopter like this one are complex, only the surface level parameters need to be studied in order for the aircraft to function. The main aerodynamic factor that needs to be minimized is the sideways cross-sectional area, as this is what directly impacts the drag generated in horizontal flight. For this reason, the bottles are set up as far into the frame as possible while still allowing space for the gravity hook and stepper motors.
This year, manufacturing was fairly straightforward for us, relying on an established quadcopter frame, 3D prints, laser cutting, carbon fiber trimming, and other techniques for frame reinforcement. In our early stages of testing, we encountered difficulties with stabilization, leading to several low-height falls, forcing us to reinforce the frame and get more hands-on with the drone's optimal design layout. Disregarding the early flights, we were able to perform about 23 low to medium height manual flight tests, which, including the total from the next section, accounted for a total flight time of approximately 200 minutes.
Our aircraft is powered by Arducopter, a specialized branch of ArduPilot designed to integrate with PIC-SOC flight controllers. ArduPilot, an open source software, autonomously navigates the aircraft based on commands from our ground control station, enabling functionalities like waypoint navigation, loitering, takeoff, and landing. We use Mission Planner as our ground control software. To enhance Mission Planner, we developed a custom web application using a Python backend and web-based frontend. This interface operates alongside Mission Planner using Mavlink communication protocols for seamless coordination. Utilizing image processing, we dynamically configure autopilot waypoints and flight modes based on real-time data. Before full autonomous transition, extensive testing and calibration in manual modes ensured system functionality. Low hover flights with 5 waypoints yielded 6 successful flights and 30 error-free waypoints. Additional autonomous modes such as RTL were evaluated, incrementally increasing autonomous capabilities. Successful outcomes led to an 82-foot fully autonomous 8.4 kilometer flight path, confirming operational readiness for competition. Static obstacle avoidance within our system is seamlessly achieved through the application of a geofence around any objects deemed necessary to avoid. The autopilot intuitively adjusts its flight path, ensuring avoidance of geofenced areas. Prior to flight, entry of static obstacles equips the autopilot to navigate around designated areas as it progresses along waypoints. These geofences have been tested in parallel with waypoints and have been successful with our current system. For dynamic obstacle avoidance, we will assign a team member to monitor UAVs and aerial objects using FAA remote ID regulations. This proactive measure provides timely warnings to the safety pilot for manual intervention if necessary. Challenges like interoperability, Canadian weather conditions, and identifying small, fast aerial targets limited dynamic obstacle avoidance developments, thus resulting in us taking this approach.
While exploring design alternatives, we prioritized cost, safety, and required acceptance criteria, leading us to our current solution. We had the opportunity to reuse our aircraft from last year, however we noticed several downsides to using a fixed-wing aircraft as mentioned previously. Not only is it more costly to manufacture, but we encountered difficulties associated with obstacle recognition for ground imaging at high speeds, payload deployment, less agility and higher turn radius, and less consistency with autopilot in our tests. Additionally, we considered instead having multiple smaller drones for a single payload deployment, but it would create difficulties for us to meet the necessary time restrictions in the competition. There could also be minor inconsistencies between different iterations, leading to even more costs. On the other hand, a single large drone such as an octocopter carrying all payload would also not be cost effective for us, as it requires significantly more materials and testing. There could also be minor inconsistencies between different iterations, leading to even more costs. This is why we ended up choosing a middle ground, balancing power requirements and payload capabilities, while keeping costs in mind and meeting acceptance criteria at the same time. Throughout development, all necessary PPE was always worn, like safety goggles, gloves, and earplugs when using any power tool. To mitigate electric shock and propeller rotation, we would only work on the drone when fully unpowered and with attached propeller straps. Special storage spaces are allocated for batteries and hazardous materials. Additionally, we always worked with fire elimination techniques in place according to chemical data sheets. During flight testing, the safety pilot announces when flight tests are being performed and ensures the field is fully clear. They also announce when the drone is powered on or off to identify when a technician can approach the drone. The technician always ensures the drone is unplugged before performing any maintenance. By going through a checklist of all hardware on board before flight, we can ensure all our connections are secure, batteries are correctly mounted, and the drone is truly ready.
Throughout the full mission testing phase, our team incrementally tested vehicle capabilities to evaluate performance. Our approach began with manual flights, where we executed manual takeoff and landings at low altitudes of 5 meters. As we progressed, we methodically expanded our manual control capabilities, maneuvering along pitch and roll axes at higher altitudes, wary of any oscillations or areas warranting attention. As we became more comfortable, we increased flight speeds from 5 meters per second to upwards of 15 meters per second. Transitioning to semi-autonomous flight, we validated the effectiveness of loiter mode, resulting in us needing to manually fine-tune the proportional integral derivative or PID settings to guarantee the quadcopter's stability under autonomous operation. We then proceeded with autopilot testing, as discussed previously. To finalize our full mission testing, we focused on compliance with the flight performance requirements. Each test was recorded and documented, with metrics being discussed in the next section. These metrics indicate proof of consistent and safe flights while simultaneously meeting flight requirements. Full flight testing with the payload winch system has not been completed due to weather constraints explained earlier. Both our flight and payload systems work in isolation, and we are confident that both systems will work once integrated. Each flight video features our safety pilot's name and the aircraft's identifier. Our safety pilot, Tanish, has experience piloting in SUAS 2023 and has all required licensing to be able to legally fly. Our initial demonstration features a 200-foot autonomous flight, highlighting our smooth transition between autonomous and manual modes. Setting a waypoint over 225 feet away, we navigate with precision, maintaining an error margin of less than 23 feet or 7 meters. Transitioning to manual mode, our pilot returns the drone for a controlled landing, demonstrating our proficiency not only in transitioning between autonomous and manual modes, but also in managing takeoffs and landings within a compact runway measuring no more than 70 by 75 feet. Our second flight demonstrates manual control from takeoff to landing, extending more than 1,000 feet away from the safety pilot. Conducted entirely manually, we have multiple perspectives of this flight captured by team members. The flight reached a distance of 311 meters or 1,020 feet away from the pilot, maintaining an altitude of 30 meters or 100 feet above ground level. Additionally, this showcases our ability to sustain flight above 75 feet while operating more than 200 feet away from the runway. Our final flight showcases an 8.4 kilometer or 5.2 mile journey with all electronics and a full payload. Opting for an autonomous navigation, we looped over the same set of 4 waypoints at 25 meters or 82 feet above ground level for consistency. The payload includes 3 water bottles as depicted in the video, where we intend to land for reloading during the actual mission. Our waypoint error is set at 7.00 meters or 23 feet to remain within the 25-foot threshold configured in Mission Planner under the waypoint radius option. Achieving 100% accuracy, we never exceeded the 25-foot waypoint error limit. Moreover, this flight demonstrates our ability to navigate within a turn radius under 150 feet and land autonomously within the prescribed 70 by 75 foot VTOL runway dimensions. This shows we will have no issues remaining within the mission flight boundary. Utilizing a quadcopter, we are able to meet or bypass horizontal takeoff and landing requirements, including angle of climb, descent angle, and HTOL runway size. Collectively, these flights meet all proof of flight and performance criteria, signaling our preparedness to compete in this year's competition.
So to summarize, we're Schulich UAV. We carefully analyzed the competition requirements to ensure our VTOL quadcopter meets the mark. Equipped with a high-performance camera, our drone captures high-quality images crucial for the competition, and our payload design is simple, ensuring stability and efficiency. Our communication hardware ensures reliable aircraft-to-ground interactions along with our autopilot system, being meticulously tested and calibrated for autonomous operation. We also explored various design alternatives, prioritizing cost, safety, and efficiency. If you'd like to contact us, please reach out to schulichuav@gmail.com. Thanks for watching.